Hi, this is a movie on statistical mechanics in which I want to explain how you can calculate the entropy of an ideal gas, and from that entropy, as we shall see, you can derive the equipartition theorem and you can derive the equation of state of the ideal gas. The general formula which gives us the entropy is S is K ln omega, where S is the entropy that we are looking for and omega is the number of states that's accessible at energy E, whereas we assume throughout this analysis that the N and the V are considered to be constant. So our aim is to calculate this omega, so we have to count how many quantum states are accessible to the system at energy E. And the system is an ideal gas, which means that there is no potential energy. There is exclusively kinetic energy. And the quantum states for a flat potential, so the potential is zero everywhere, they are given by plane waves, e to the power I k dot r, and this is a normalization factor. Now we assume that the volume we are looking at is a L by L by L cube with periodic boundary conditions. That may not seem the most relevant type of boundary conditions for experiments where the boundaries are usually fixed, so the wave function vanishes there, but it turns out that whether you consider periodic boundary conditions or you consider fixed boundary conditions, it doesn't matter. For the entropy you always get the same result, and here I use periodic boundary conditions mainly for mathematical convenience. Now if the boundary conditions are periodic and we have these plane waves, then the case should be should assume values only 2 pi over L times nx, ny, nz. So k is a three-dimensional vector and it has this prefactor, and then the nx, ny, nz are just natural numbers. So the nx is 0, and this also for the y or for the z. They can be 0, 1, 2, etc. So the k vectors that can be occupied, they lie on a cubic grid of k points with a grid constant of 2 pi over L. Now we prefer talking about the momenta rather than the k vectors, and the relation in quantum mechanics is that P is h bar k, where h bar is Planck's constant. And now we have a cubic grid of p points with a grid constant 2 pi over L times h bar, and we can also write that as h over L, where h is now the bare Planck constant. Now we have n particles in total, and each particle has a momentum which lies on this cubic grid, so they can be labeled as pix, piy, piz, and so we can lump those all together into a 3n dimensional vector which is called capital P, and that lies on a 3n dimensional cubic grid. And so each point on that 3n dimensional cubic grid defines a state of the n particle system. Now if we calculate the energy, that's the sum over the pi squared over 2m, and that's the same as the length of this vector squared, of this capital P squared, divided by 2m, and that condition, if we now want to consider all the states which have a fixed value of the energy, it means that they have a fixed length of this vector, so this defines a hypersphere in 3n. Remember that we had to count how many states there were available at this particular energy, so we have to look at the number of points on the cubic grid that where the hypersphere in 3n passes through. But now we have a problem, and that problem is indicated here. So this is a two-dimensional grid, and it has a certain grid constant, and I draw a sphere. But the sphere is infinitely thin, the points are infinitely small, and so the intersection generally is 0. And in order to fix that problem, that the intersection is typically 0, we make use of the fact that the measurement accuracy is always finite, and therefore we do not consider states with energy exactly at this energy at E, but we consider them in a narrow band between E and E plus delta E, and we can of course relate this E, this spread in E, this delta E, we can relate that also to a spread in the P, so in the length of that vector. And that means that we have not a spherical shell which is infinitely thin, we should need to consider in 3n dimensions, but we have a shell of a finite width, a finite thickness. And in order to count now the number of points that are found in that finite thickness shell, we first look at the volume of a sphere in 3n dimensions. And you can find that volume in math books, and you can find it on Wikipedia. And it turns out to be given by pi in the power 3n over 2, p in the power 3n over 2 plus 1 factorial, and that then this p here, that's the radius of the sphere. Now we are not interested in the number of points inside the sphere, but we are interested in the number of points in the spherical shell with thickness dp, and we can find that by taking the derivative of this volume, and then we multiply by dp, so this is the volume of the spherical shell, so this is the shell volume. And now we realize ourselves that on this cubic grid we are looking at, each point occupies a volume of L over H, or H over L in the power 3n, because H over L is the grid constant and we are on a 3n dimensional grid. So if we divide by that volume, and that's what we do here, we have the number of points inside the shell. And so the ON, that's the number omega n, that's the number of states inside this shell, can be given by this expression. And if I want to make it really, if you want to do this really correctly, I need to multiply here by dE, small energy width. And then we have this formula which is correct, and for the volume here we take the derivative of this expression. Now, having the omega, we can find S just by applying S is k ln omega, and then we find the following expression. So it's all mouthful, and you can see that this term, it scales with n, and then even the logarithm of v, there is here an e, there is here a 3n, etc. So all these terms, they scale in some way with n, and this is just my finite width. And so if we take delta p of order 1, this is a number which can be neglected with respect to all the other terms. And so the final result is then this expression here. Having that expression, we can check whether it really makes sense by taking this S, as it is given here, and calculating the SDE at constant nv, and we know that that should give us 1 over t. It turns out that if we do the math, you get this result, and from that we immediately infer that E is 3/2 times nkbt, and that's the equipartition theorem, which is well known for ideal gases. And from the equipartition theorem, it's easy to see that Cv, which is also dE dt at constant n and v, is given as 3/2 times nkb. Now, another important result that we can derive is the pressure. Is for the pressure, we can find an expression for the pressure. P over T is ds dV, so now we take the derivative with respect to V, and then we find the equation of state for the ideal gas. So this is the equation of state. So everything seems to be fine. However, it turns out that the s that we find in this way is not correct. And the reason can be seen when we write s in a slightly different form by writing all these terms inside the logarithm as separate terms. And then we see that s is kb times n, and then we have a series of terms. And if we scale up the system, so we scale up v and e by a factor of 2, then we see that this term scales up by a factor of 2. This term scales as well, and all these terms do not scale. So imagine e and n are multiplied by 2, then of course the fraction doesn't change. And so we see, however, that this term gives you a contribution in that case. So in particular, if we go from nve to 2n2v 2e, s should go to 2s. But if I do the math for this expression, it turns out that if I scale up all these guys, that I do not only get 2s, but I get an additional contribution, 2kb n ln 2. And this is known as the Gibbs paradox. And the solution to the Gibbs paradox comes surprisingly from quantum mechanics, because the atoms are identical particles in my gas. And if I interchange two particles, then according to quantum mechanics, I get exactly the same state. And so we have overcounted the number of states in my system. So to make that clear, suppose I have two particles and they have two momenta. So one-dimensional system, two particles. One particle has a momentum p1 and the other one has a momentum p2. Then I am, for example, at this particular point. But if I swap the two values, I will have this point here. And so far we have counted those as two different points. But according to quantum mechanics, this is just this boils down to interchanging the two particles, and for indistinguishable particles, these points should be counted as one. And so in general for n parts, so in this case I should divide by 2 factorial, because that's the number in which I can order two particles. And in general I have to divide by n factorial. And if you do that, so then you get the quantum mechanical entropy, which is the classical entropy we just calculated, but I get an extra term. I get minus the logarithm of n factorial. And using Stirling's formula, which says that n factorial taking the log gives me n log n minus 1, the entropy turns out to become this expression. And the difference between the previous one is that here I have now not a v, but a v over n, and here it used to be a 3/2, and that's now a 5 over 2. That derives from this 1 in Stirling's formula.